Jai Hind everyone, I am Mohan Sharma, Assistant Professor from Electrical and Electronics Engineering Branch, AKGEC Engineering College. This is video lecture for Power System Operation and Control. Its AKTU code is KEN070. In this video lecture, we are going to discuss about several voltage control techniques, and basically we will talk about the active power and reactive power compensation techniques over here. So let's start. So you know that a power system is basically said to be well designed if it gives good quality of power to the customers. So if I'm the customer and I'm actually trying to buy the power from the utility, so what will be my requirements? My requirements will be a constant power which is available to me and uninterrupted supply. So basically if we talk about the quality of the power, it is basically reliability, right? So how the reliability is defined? So we can say that we are getting a constant power supply for a continuous time period. So we can say that yes, that company is reliable to me. So that's the point over here. The power system is said to be well designed if it gives a good quality of power, that is good quality of reliable supply, right? Now we have several equipments connected into our system. So all the equipments on the power system are designed to operate satisfactorily only when the voltage level of the system correspond to their rated voltage. This is the important one. So you must have a rated voltage, or we can say that in the practical scenario, the rated voltage, obviously it is very hard to maintain rated voltage for a long run of time. So we say that we can have the voltage within the 5% limits, right? So we must have a constant voltage, or the voltage variation should be in the limits of 5%, right? So any equipment, if you talk about any appliances, so any equipment works well or with the highest efficiency when it operates under its rated condition. So we must try to operate any appliance under its rated conditions only. If the voltage variation is more than a prescribed value, the performance of the equipment suffers and the life of the most of the equipments are sacrificed. So what is the drawback if we operate a system or operate any appliances in underrated condition or overrated condition? So definitely it is not the well maintained condition for operating that particular machine. So yes, obviously it will be deteriorated, the operation will be deteriorated. So we can say that the performance of the equipment will suffer, and also the life of the machine or life of the appliance would be reduced. So you must operate any machine or any appliance within the prescribed limits, or I must say it must be operated on the rated conditions only. Now we have several power system control methods. So see, basically if we talk about the power system control method, basically I am talking about the uh, real power, reactive power, frequency and voltage. See, there are 4 parameters. Okay, now among these 4 parameters, we know that the power consists that S is equals to P plus JQ, that is apparent power, real power and reactive power. So we know that these two powers are important one over here. So real power can be controlled with the help of frequency, and active power can be controlled with the help of voltage. So here we can see that PF is real power and frequency control method. So this is active power control method or frequency control method. Similarly, we have QV control method, so it is reactive power control and voltage control method. So reactive power control method, we will talk about these methods in detail over here. And by controlling the reactive power, we can control the voltage of the system. Similarly, by controlling active power, we can control frequency of the system, right? Now if we talk about the control of the voltage control, see, we have a generator over here. See, this is generator, this is bus number 1, this is bus number 2, and they are having voltages V1 and V2. Let's say over here, this is V1 of the bus voltage, V2 of the bus voltage, and the reactance of this transmission line run over here is JX. Let us say that a load is connected over here, and load connected to the source through a line. So this is source, this is transmission line. Let us say that this load is connected over here. Basically load will be connected to the bus only, not over here. This is L, right? So if we talk about the voltages over here, so what will be the voltage voltage over here? So V2 is V2 will be equals to V1 minus, that is this one, this V1 is equals to the voltage which is generated over here, plus basically the drop over here will be subtracted, since we will get the rest amount of the voltage over here V2. So V2 will be equals to V1 minus Qx upon V1 minus JPX upon V1, right? Similarly, we can have its simplifications. So we will have V2 is equals to V1 minus Qx upon V1, right? Now we are having several methods of voltage control. So there are several methods. So among those methods, first one is shunt capacitor or reactor. That is, we will be connecting a capacitor or let's say a reactor into the shunt of the either load, right? So we are controlling the reactive power reactive power of the load over here. So that's why we can say that it is shunt capacitor. Similarly, we will be having series capacitor method, so in which the capacitor will be connected in series with the load. Then we will be having synchronous capacitor. So it is basically the synchronous machine, that is synchronous motor operated under a special mode of operation. We will talk about this in later. After that, tap changing transformer, we are having several transformers, just like auto transformer is there, in which we can have several tapping. So depending upon the requirement of the voltage, we can just have the minimal amount of prescribed amount of tapping, so that we can have the whatever the amount of voltage is required, we can have that voltage. Lastly, we will be talking about booster transformer, right? So the function of booster transformer is same as that of the tap changing transformer. So first is shunt capacitor or reactor. Basically, capacitor is condenser or capacitor, it is known as condenser also, and reactor is basically inductor, right? So what you will do, you will just it is a shunt capacitor, so you can connect this capacitor. This is shunt connected, right? Here load is connected, so in parallel with the load you can connect a capacitor. Now what is the function of this capacitor? Capacitor will provide the reactive power to the load, whatever the reactive power is required, right? Now the shunt capacitors are used for lagging power factor circuits. So wherever you are having more of the lagging power factor, under that condition you have to bring the power factor to the 1, so that you can just have the unity power factor over there. So you have to compensate the lagging power factor. Lagging power factor has to be compensated, so that it can be bring back to the unity power factor. Although not only unity, it can brought back to in the range or very much near to the unity power factor, right? So shunt capacitors are disposed along routes to minimize losses and voltage drops or light loads. When the voltage is high, the capacitor output is large and the voltage tends to rise excessive level. So basically what happens, this is what should I say, it should be like a analogy of Ferranti effect, right? So if you are having a no load condition over here, so if a very lightly load is connected over here, or let us say if no load is connected over here, so what will be the case? See, this is capacitor. This capacitor is basically injecting the reactive power to this load, right, in the form of electrostatic field. So now the voltage is this power is injected into the load. Now if you see that the load is very much lightly load connected, so no load connected or lightly load connected, under that condition the voltage over this circuit or this point increases excessively. So that's what it is given over here, voltage tends to rise excessive level. So this is actually the case of Ferranti effect. Same effects happen when you have long transmission lines, and under those long transmission line, when you have less load connected or minimal load connected, under that condition the voltage rises very much higher on the higher limits. So that's why we can say that the voltage increases due to this effect. Similarly, shunt reactors are used for leading power factor circuit as in the lightly load condition. So shunt reactors will are just the contrary part of the shunt capacitors. So whenever you have capacitive load or leading power factor, you can just compensate it with the help of this one, reactors, right? Now, what is the location of the shunt capacitors or shunt reactors? So basically, shunt capacitors are used on the load ends. Basically, they are connected to the load end. So just we have seen that one of the figures in which the shunt capacitor was connected at the load end side, right, of the power system, and are applied in variety of ranges. Shunt reactor may be permanently connected, so we can have a permanent connection of the shunt reactor. So reactor is basically inductor that I have already told you. When this reactor is connected, so there is no harm in connecting this reactor permanently to the circuit. So it can be connected permanently, and if it is not utilized, if you don't have higher amount of capacitive load, so it will be having no use. But in the short circuit, we know that the reactor acts as in the steady state, reactor acts as short circuit. So there is no harm in connecting this in permanently to the circuit, to the line, limit temporary over voltage and switching transient. So it is also applicable for preventing the this switching transients also, right, because it doesn't allow sudden change of the current. That's why we can just use it as prevention of the switching transients, right. It may be connected in the EHV bus or to the tertiary winding of the adjacent transformer. So basically we have tertiary windings in the transformer, so that's why we can also connect it to the windings of the transformer, right. Now, application of the shunt capacitor, where it is applied. So firstly, it is we can see that it is applied on the distribution system. So this one is the plant compensation technique. You can see over here there is a transformer, and 1 and 2, there are two shunt capacitors connected over here, right. So this is plant compensation. See, this is individual compensation. In this you have first machine, you have second machine. In this this one is capacitor which is connected into the shunt portion. Similarly, this is a group compensation, in which you are having a group of machines which are sending power or basically receiving power. So under that condition, you can connect this capacitor into the parallel. So we can say that this is group compensation technique. Similarly, this is the power factor correction in the industrial power plants, right. Second one is the transmission system. So here in the transmission system, we have a transformer over here, and this is basically tertiary connected capacitor, which I just was talking about. See, these are the primary winding, secondary winding, and this is tertiary winding, and you have 1, 2 and 3 shunt capacitors connected individually to the this one, right. Or this is transmission system in which the tertiary connected capacitor banks are connected, so that the power factor can be improved over here. Next one is series capacitor. Just like we are having shunt capacitor in which this capacitor is connected into the shunt parts. In this one, it will be connected in series, just like this one. This is connected in series, right. Now these are connected in series. See, this is connected in series with a line conductor to compensate for the inductive reactance of the line. So its main aim is to control the inductive reactance of the line. So what is the case? It reduces the transfer reactance between the buses to which the line is connected. So whatever the transmission line is over here, so the inductive reactance over here is basically compensated by the help of series capacitor, right. And it increases or maximum power that can be transferred and reduce the reactive power losses. So whatever the losses are, they can also be reduced, right. Then what is the location of series capacitors? So we have let us say 3 positions. So firstly, we can connect the series capacitor in midpoint of the transmission line. Let us say we are having 100 km of transmission line. So under that, we can connect one of the capacitor on 50 kilometers of the distance. So that is actually the location, this is the midpoint of the transmission line. Now second one, we can connect the this capacitor onto the line terminal, that is to the last of the terminal, that is to the end point of the transmission line, just like to the 99th kilometer or 100th kilometer, wherever the load is connected over there, right. After that, we can connect it to the 1/3, that is at the 66 kilometer distance, or the 1/4 of the transmission line at let us say 75 kilometer distance. So and these are several distances under which upon which the capacitor can be connected, so that it could work effectively, right. Now what are the applications of the series capacitor? It can be applied under two conditions, firstly it is under the distribution feeder. So wherever you have a distribution system, under that condition this capacitor can be utilized, or we can utilize it in EHV transmission system. So wherever extra high voltage transmission systems are there, under that condition you can connect this series capacitors. Now there are several advantages and disadvantages of these techniques, so we will talk about advantages first. So if load VAR requirements is small, series capacitors are of little use. So if you require less amount of reactive power, so under that condition series capacitor are of, I would say, no use, right? If voltage drop off is the limiting factor, series capacitors are effective. Voltage fluctuation due to arc furnace are also evened out. Okay, so whenever you have arc furnaces, so under that condition voltage fluctuation is the most occurring phenomena over there. So if you just install this series capacitor or a shunt capacitor, what you can do, you can just omit these voltage fluctuations from the arc furnace, right? And next one is if the total line reactance is high, series capacitors are very effective and stability is improved. So if you know that you are having a load in which the line reactance or the transmission line reactance is very high, under that condition you just connect a series capacitor, and under that condition this capacitor will compensate the high reactance of the line and improve the stability of the system. Okay, along with the advantages, there are several one of the disadvantages also. So the major drawback of the series capacitor is high over voltage and produced when a short circuit current flows through the capacitor. Similarly, if you know the capacitor is connected in series, so under that condition, if a short circuit current, obviously the short circuit current is having a very high amount of current, that is the magnitude of the current is very high, and if that short circuit current flows through the capacitor, what happens, this will produce a very high amount of voltage, that is the voltage overshoot, that is higher amount of voltage will be there, right? So this should be avoided. Then we'll talk about the synchronous condenser. See, synchronous condenser is basically a synchronous motor which is running in overexcited condition. Okay, overexcited mode. So basically there are three modes of operation: under excited, normal excitation, and overexcitation. So when the synchronous motor is operated under overexcitation mode, this acts as a synchronous condenser. Why synchronous condenser? It just provides the reactive power to the system. Wherever it is connected, it just delivers the reactive power. So this synchronous motor is a very important machine, very special machine, right? So the synchronous motor running without a mechanical load can absorb or generate Q, right? So it can absorb, then if I'm saying that it is absorbing, then it is acting as a lagging load, and if it is delivering Q, it is acting as a capacitor, right, depending upon the excitation, right? So its excitation is very much important. Now, as a synchronous motor losses are considerable compared to the static capacitor, the power factor is not zero. Why? Because the motor is having some rotating part. Under that part, losses will be there, and we cannot omit the losses to the zero. That's why we can say that the power factor of this machine is not zero at all. Now, when used with a voltage regulator, the compensator can automatically run overexcited at the times of the higher load and underexcited at the lower load. So we can just omit the situation of being underloading and overloading just by connecting it with the help of a voltage regulator. So if you are having a voltage regulator, compensation of this one, this compensation technique, you can make it automatic. So automatic means that whenever the higher load is there, so under that condition it will be overexcited automatically, and whenever the loading condition is lightly, under that condition the machine will automatically go into the underexcited mode, right? Now we can say that the advantage of synchronous compensator is its flexibility of operation for all loads of conditions. So if we are having a number of yes, obviously we know that the load profile continuously changes, and in the fractions of second it can be converted from leading load to lagging load. So under that conditions you can have a automatic or this automatic synchronous condenser, so that you can have regulated control of the power over here, right? Then advantage and disadvantage of this synchronous condenser. So firstly, the advantage is that the magnitude of the current drawn by the motor can be changed by varying the field excitation, so it gives a control power factor. So just by controlling the input current you can just control the power factor. Basically we are just controlling the excitation. Current is just a byproduct, we can say that. So just controlling the excitation, you can have in the mode of operation change to lagging power factor controller to leading power factor controller, right? Now the motor winding should have high thermal stability to the short circuit. So these windings have higher thermal stability so that it can overcome the short circuit current. The fault occurring in the motor is easily removed. So it is very much obvious that this one fault in the system or this motor is removed automatically, right, or very easily. And it having disadvantages like it requires more maintenance. Yes, more maintenance cost is high, as well as its maintenance cost is high, right? The number of maintenance requirement and cost of maintenance both are on the higher side. It produces noise, although it is a motor, so definitely it is going to produce some noise. Okay, considerable losses are occur in the motor. So yes, it is a mechanical device, rotations are there, rotor rotates, so mechanical losses will be there. Now we'll talk about some static compensation techniques. So this is SVC, that is a static VAR compensation technique. So SVCs, what are SVCs? They are the shunt connected static generator and absorber whose outputs are varied so as to control the specific parameters of the electric power system. Basically it is controllers or static generators in which there are no moving parts. Those are connected to the system so that they can absorb the output whose output are varied, so that it can have a static performance over here. Now okay, so it has no moving or rotating parts. So just like I said, there are no moving or rotating parts, so that's why they are known as static compensators, right? So there are several static compensator in which we are going to use our power electronic devices, just like thyristor, SVC, SCR thyristors, or all these things, right? So although all these things are same, so there are several types of SVCs. Firstly is a thyristor controlled reactor. We'll talk about this. Thyristor controlled capacitor. Okay, then thyristor switched reactor, that is TCR, TSC, and the thyristor control transformer. So all these four types of SVCs are there. So this is the basic block diagram of SVC, in which we have this high voltage bus over here, LV bus, PT, that is potential transformer, automatic voltage regulator, thyristor SVC controller, thyristor firing circuits. These are thyristors connected over here. All these are thyristors, right? This is capacitors which are controlled by this thyristor circuits, TSCs, right? Thyristor switch capacitors. And this is the reactor part which is connected over here. And all these circuit, basically this is the controller part of the Q, and which is transmitted over here to the high voltage bus. And the firing of this thyristor is controlled by this thyristor firing circuit, right? So this is basic block diagram by which SVC works or operates. Now ideal SVC SVS is basically HVAC, this in which we have a variable inductor and variable capacitor. So this is the ideal diagram in by which we can control the static that is Q over here, right? That is reactive power, right? Now we have characteristics of realistic SVC. So this is shunt reactor, this is for shunt capacitor, and this is basically the combination of capacitor and reactor both. So here we can see that these are controllable reactors are there. This is variable reactor, so under that condition we can change the value of the reactor over here, so that the power input to this this voltage is basically controlled. So we can have, this is voltage versus I current, I characteristics, V versus I. In this this is the maximum L which can be attained over here, and this is the minimum well, and this is the slope of this one, right, Ks. Okay, similarly we have a static capacitor. This one is fixed over here, so this is fixed capacitor technique, and under this we can have V versus I characteristics. This, although this is on the opposite quadrant, because we know that in inductor or capacitor, both these quantities are basically in opposite directions, right? So we are talking about the phasor diagrams over here. So this is the why it is fixed, because it is this is a straight line on there's no range given over here. Why? Because this is of fixed nature, right? And lastly, we can combine both these characteristics so that we can have this one. This is capacitive and this is inductive, and this is SVS, and similarly this is for capacitor and this is for inductor. And finally what we will get, the characteristics is basically this one. Final characteristics comes out to be this one. Okay, so this is the final characteristics. Now tap changing transformer. So what is tap changing transformer? Basically yes, this is a tap changing transformer over here. So you can see that we have this one is to TS and TR is to 1. See what is happening over here. This is the primary side, or we can say that this is a transmission line, this is the sending side, and this is the receiving side. Okay, so what you can say, this is the sending side voltage. So there the capacitor or the transformer connected over here, you can see that this is the primary winding, this is the secondary winding of the transformer. Under this condition, secondary is connected to the sending side of this transmission line, in which voltage is V1 over here, and the primary side of this one is connected. See, here are tappings, this is, they are known as tapping. So there are several, or these tappings are connected to the internal portions of, or the number of turns of the winding. So we can see that if this key is connected to this one, we can have the full winding availability over here. If you connect this over here, so we can have only this portion of the winding available over here. So depending upon the situation, we can just control the tappings over here. Similarly, the tappings can be connected control over here. So whatever the amount requirement is there, you can just connect these tapping to any one of the taps over here, right? So this is the transmission line over here which runs, and its impedance is given by Z over here. Voltages are Vs, sending side voltage, V1, V2, and this is the receiving side voltage. And finally load is connected over here, and current IL or IR, whatever you can say, is flowing to the load side, right? So this is how the tap changing transformer operates, right? So the voltage control of the transmission and the distribution system is obtained by tap changing transformer. Similarly, the tap changing are either on load or off load changer. So we can have this taps taps available on the primary side or the secondary side of the transformer. They can be controlled on load as well as off load, right? By changing the turns ratio, what we are actually doing, we are changing the turns ratio. Turns ratio is N2 upon N1. If you are changing N1, that turns ratio automatically changes, right? So by changing the ratio of the transformer, the secondary voltage is changed, and thus voltage is increased or decreased as per the requirement, right? So lastly, we have booster transformer. So what is a booster transformer? The two winding transformer, the two winding load tap changing transformer performs two functions, and transforming the voltage and boosting the voltage. So transforming the voltage is basically as per the requirement, the voltage can be transformed, right? So it can be increased or it can be decreased, whatever the requirement is there. And boosting the transformer is basically, boosting the voltage is actually the raising the voltage level, right? So you can raise the voltage level to a limit only, right? Now what is the location at which the booster transformer is installed? You must have seen there are several location in the transmission system where you might have encountered some transformers. There are basically a small size of transformer installed alone into the transmission line, and basically that is known as booster transformer. It's main aim is to just increase the value of the voltage. Or you might have encountered these transformer on the railway tracks, right? Whenever the railway tracks are there, you might have seen a transformer connected in between. So that is basically the booster transformer, and the work of that booster transformer is to just enhance the level of the voltage. Why enhancing? Because it works just like the transmission system, in which there are there is a very long line which is connected over here, so from which the pantograph is connected, and the load, as per the load, the current or the voltage decreases as the distance between the two transmission or power providing utilities is increased. Under that condition, the voltage has to increase. So under the for increasing the voltage or for raising the voltage level, a booster transformer is utilized or installed at several locations, so that the voltage level can be maintained, right? So it can be installed at a substation, intermediate point of the line, or voltage regulation. So there are the actual locations at which it can be installed, right? So this is actually the booster transformer. Okay, so this is how it operates. So lastly, we can say that synchronous condenser is better to overshunt and series compensator if we need wide range of operation. Obviously, motor gives wide range of operation, and SVC is more beneficial as it does not contain any rotating part. Obviously, if rotating parts are absent in the system, it will have very less amount of losses. Although it will be having losses, the losses are drastically reduced, right? So this was all about voltage control. Thank you. Jai Hind.